in an octagon, how many quadrilaterals can we draw? So we draw out an octagon, eight vertices, and we connect them. You know, you can, this is like one of these questions you might have seen on Facebook, like how many shapes to see in the big shape. One quadrilateral I can draw would be like this. Another quadrilateral I can draw would maybe be like a rectangle, like here. Or yet another one might be some sort of weirder sort of quadrilateral. It doesn't have to have, could be like something like this. So what do you guys think? How can we, you know, it would be really difficult to draw out all of these shapes. So what tool do we have that can help us count the number of quadrilaterals that we could actually draw? Does anyone see what we can do? Anyone have it? And you can message me your idea also. If I want to count the number of four-sided shapes I can make out of the octagon, what tool could we use? What do you guys think? Any thoughts? Well, what does it take to make a quadrilateral? We got to, yeah, exactly. Yeah, we got to start with just picking, anytime you make a quadrilateral, what you're really doing is you're just picking four dots. So, for example, this quadrilateral, the green one, consists of, I'm going to do it in green. The green one consists of picking these four dots out of the 8. So every quadrilateral you pick corresponds to a choice of 4 dots. But Dimitri, what do you mean by that? So Dimitri, you wrote something I really like. So Dimitri said 8
if you were to
4.
grab the ones on, like, for instance, all the ones on just the farthest. Oh, I guess never mind. Oh, neat.
Yeah. So you're saying to grab if you grab all the ones on the far left, you're gonna.
For some reason, I was thinking it had to be a rectangle.
Oh, no. Yeah. Any quadrilateral. That's right. Rectangle's maybe a little bit trickier. Maybe not too bad, but yeah. So you just do 8 choose 4, and just to review that, that's like picking out of 8 friends, we got to pick 4 of them to go to the movie with us. There's 8, 7, 6, 5, all over 4, 3, 2, 1. I like to do, when I calculate these, I like to, if I see some numbers that multiply to something in the top, I just like to clear them all out right away. So I see the 3 and 2 cancel out with the 6. Then the 4 and the 8 cancel, giving me a 2. So overall, I get 70 different quadrilaterals. And this is a really nice way of thinking about connecting, counting things in geometry with just thinking about, oh yeah, all you're really doing when you're drawing a quadrilateral is you're specifying the corners. It's really just like picking friends to go to a movie with you. That's all. Okay, so based on that, and if you have that mindset that, oh yeah, like drawing shapes is really like just picking two things, and you don't care what order you pick them in, you just care about which ones you pick. So if I pick these 4 friends, I'm going to get the same rectangle or the same quadrilateral no matter what order I pick them. There's only one rectangle that has these 4 dots. Now, what about diagonals? How can we apply this idea to diagonals? How many diagonals, let's say, in an octagon? So I draw it again. And this one's very similar, but there's just a slight detail you have to be careful with. But the main idea is almost identical to what we just did. Do you guys see how we can think of this? And by the way, diagonal means it's a line segment that connects 2 dots, and it has to go through the inside of the shape. It can't be on the edge. So how do we do that? How do we count the number of diagonals of an octagon? So there can be like this one. You can also do something like this. You can do something like this. What do you guys think? Diana, very good. Diana, what did you suggest?
Since you said it was similar, I just thought since the diagonal has 2 points connected, it'd be 8 choose 2.
Yeah, perfect. Right? Every 2 points you make, you get like a little line segment you can draw. And you don't care what order, it's still going to give you the same line segment. That's perfect. So you do 8 choose 2. Now, Diana, how do you think we would handle to actually find diagonals? Not just any pair of points, but we specifically want diagonals. So how do we adjust 8 choose 2? What do we need to do?
Like how do we figure the answer out?
Yeah. So 8 choose 2 is not exactly correct. It's very close though.
Oh, okay. Then I'm not sure.
Do you subtract 8 because the sides?
Exactly. 8 choose 2 also includes this blue one. I'm going to draw it here. It includes the edges, right? Because that's 2 friends you can pick to go to the movie with you. They happen if they're on the octagon right next to each other, that would be included in 8 choose 2. But we don't consider that a diagonal, that's considered an edge because it's on the border. So you just subtract 8. This is just like a unique thing about counting diagonals, just have to adjust that. And then 8 choose 2 is 8 times 7 over 2 times 1 minus 8. And this becomes 28 because this is a 4 minus 8, which is just overall there's 20 diagonals. Okay. Any questions? Well done, Diana and Dimitri. Thank you. Any questions on this one? So I want to kind of bring up an idea that Andrew had. I think Andrew, you're actually heading in the right way. How did you approach this one? You mentioned something about adding, and there's an interesting thing you can do with adding.
How I approach the diagonals in an octagon, I started with making a hexagon actually, and then figuring out that so I could learn the principle for the octagon.
And did you just like do it? What did you do for the hexagon?
I did 6 plus 5 plus 4 plus 3 plus 2.
Awesome. So one thing you can do with the hexagon, let's see, this is yeah. So one thing you can kind of observe with the hexagon is if you want to count the number of edges overall, you can do this. You can connect these 2 dots. You can connect these 2 dots. You can count from one edge. So this guy has 5 connections he can make. Right? Then the edge that's going to be, let's say, clockwise 1 step, the vertex that's clockwise 1 step, well, how many connections can that new vertex make? How many new connections can it make? How many like new friends can it shake hands with? Well, it's going to be just 1, 2, 3, 4. This guy can do 4 connections. It can't go back because we already have that. But everything else it can do. And it's the same thing for the next one. I'm going to put it pink. This vertex, it already has 2 previous connections, but it can make 1, 2, 3 new connections. This one can make 2 new connections. This guy can make 1 last connection. And once you get back to the last one here, you're going to be stuck. So there's no, everybody's already been connected once you get to that last vertex. So if you can count them like that, what you observe is 5 plus 4 plus 3 plus 2 plus 1. If you add up all these numbers, what you get is 6, 6, 2, which is 15. So you could have also gone 15. Does anyone see another way you could have gone to number 15?
Four and 1 is 5. 3 and 2 is 5. 5, 10, 15.
Oh, using combinations.
Ah,
There's a simple way we could have counted. This is kind of like if you're just counting all the possible edges you can draw, including the boundary.
would it be 6? Choose.
You're right there. Yeah, we're just counting pairs you can make. So what should we do? 6 choose
2.
2. And 6 choose 2 is exactly 6 times 5 over 2 times 1. So that's a neat thing that anytime you want to count the number of handshakes out of like 7 people or something, it's related to adding up all the numbers in order, the consecutive numbers from 1 to 6. And you can get a nice formula. So there's some really nice patterns. There's another way to also solve the diagonal one, which is kind of neat, where you look at each. The other formula is n minus 3 times n divided by 2. If you look at kind of how, if you do n choose 2 minus n, this is the way that we did it, but if you look at it, you can actually get it to look like this. And there's a really nice interpretation of this one. So as a challenge, try to see if you can interpret what this formula means in terms of counting not any edge, but let me kind of say but counting all of the interior diagonals, so counting all of these guys. So for the octagon, it would be 5 times 8 divided by 2, which is also 20. So this also works for the octagon and everything else. Does anyone see an explanation, just without algebra, but like, why does this formula work for calculating the number of diagonals? Does anyone see a way to interpret this formula? And if not, I'll leave it as a challenge for you guys to think about it. It's a really nice explanation, just from the picture. So one way to do it for counting diagonals is to do n choose 2, which is all the possible pairs, and then take away the edges. But another way to think about it is n minus 3 times n, all divided by 2. You know, it's a nice way, a nice way you can see that. And it's, I'll give you a little hint here. How many red lines do you guys see in this picture? Nice, 5, right? If I do that over here, and why is it 5? How could you have expected it without, like, let's say I have a 20-sided figure. Why is it going to be, how many like red lines would I be able to draw with a 20-sided figure? Okay, how do we get 5? Without drawing them all out, how could you know that I can make 5, like from that point, I can connect it to, I can make 5 diagonals, just connecting to that. Nice, yeah, exactly, I just subtracted 3. And in particular, the 3 things I subtract from the number of dots is I can't connect to myself, so that guy's gone, and I can't connect to the 2 adjacent dots. But every other dot I can connect to. So that's why you have n minus 3. And you can do that at every single dot. So overall, there's n of them. But the only problem is, like, once you get to this dot, like right over here, like once you get to, like, let's say this dot right here, if you were to try to count this one, you know, count these 1, 2, 3, 4, 5, you would see that this guy, this edge has two ways of being counted. It's going to be counted once going this way and once going that way. So that's why we divide by 2. So that's another interpretation. I personally like this one more, but if you see it this one as well, you can explain this. You can also. So and it's nice to see how they type it. All right, let's do one. Do you guys have any questions on these? Andrew, do you see now kind of how your approach was actually a nice idea? There's a connection between adding up numbers and choosing 2 of them. Choosing two pairs or something. A pair of 2. Yeah. That's a really cool connection. I'll show you an even crazier connection by the end of class.
The kicker was that once I figured out that, I did it for the decagon or whatever, and then yes. I just messed up the adding somehow.
Oh, you did the adding pattern for the decagon, but the adding went wrong?
I forgot to subtract. I think I forgot to subtract 12 at the end.
Okay, but anyhow, most important is not to do it with the adding approach, but to see that you can use combinations here.
Yes.
But it is cool to know that, oh hey, the fact that they're the same thing is a neat pattern. Really cool. I'm happy that you saw another way of doing it. Okay. Last thing I want to go over, and then we'll go over. I'll show you some really amazing patterns. Is finding the constant term. And I'm going to do this the way you can approach it on a test. The way that it kind of is looks a little bit cleaner to me. Okay. So, what if I have x x to the 5th minus 2 all over x to the 15 raised to the 8th power. Let's just think about that for a minute. This is a pretty crazy looking thing because usually we have like a simple thing here, like 2x, and then maybe just a number, regular number, or something with a y. But this is x to the fifth, and this is x to the 15 in the denominator. And so what happens if you don't need to go through this, like if you actually want to solve it right away, but I'm just going to show you, I want to do a careful thing just to get you warmed up on how it's going to look like in general, what the expansion will look like, what to anticipate. So when you FOIL this out, what's the very first term we should get? What do you guys think? Yeah, what is the, when you FOIL this, when you expand it with binomial theorem, what would be the first term you would get? Nice. Right, Dimitri, nice for that. Yeah, Colette, what do you say there?
I did 8 choose 0 and then x to the power of 40 because, well, yeah, first of all, you do 8 choose 0, 8 choose 1, and so on for all of them. And then we already have x to the power of 5, and now we're doing and now we have this 8. And so 5 times 8 is 40.
Excellent, nice, yeah. So you do x to the 5th, next one will be x to the 5th to the 7th, and then, oh, I'm going to do a plus here, just to make, I don't want to do minuses. And then 2 over x to the 15th, and then you keep going, and then the last one would be 2 over x to the 15th, but all of them would be to the 8th. This would be all added. Right, so there's a bunch of different terms. And then when you write it out, you get things like this. You get x to the 40th. Just a thumbs up if you're comfortable with kind of simplifying exponents like this and working with exponents of exponents. Is that okay that x to the 5th to the 8th comes out to x to the 40th? Any questions on this? So try this one. How does this simplify if you only use positive exponents? So you're only going to have x to some power in one spot. Everything else is going to be a number. So let me know what you get for this.
For exponents like the 5 and 7, is that additive?
Yeah, so, okay, very good question. So when you're thinking about these, one thing is to think about what it means, right? So x to the 5th to the 7th, right, is going to be x to the 5th times x to the 5th times x to the 5th, and so forth. So if you just try to break it up and look at how many x's do you see, how many would we see overall?
7.
Oh, I mean like each of these is also x, 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 x. So overall,
7 times 5.
Exactly, that's right. So for that rule and these rules with exponents, I really encourage students, anybody, yeah, so in my last class, when we covered exponents and stuff and learned these laws of exponents, which I know you have seen, I see a lot of people asking like, oh, should I add or multiply here? What rule do I need to use? And my response is always, try to, it's okay to forget and like have to think about it for a moment, but always make sure you can justify. And one thing that does help me is I think of simple, especially when it's like more complicated numbers, but when it's like 5 and 7 especially, I actually try to visualize the x's and actually see what's happening. Because you would agree, Andrew, like, what about this? X to the 5th times x to the 7th. What pattern do you want to use there? And can you actually visualize all the little x's? What exponent would that be? This would be x to the 5th. But if the two powers are multiplied, you actually would just have 5 x's here and 7 x's here, and you put them all together, you just get x to the 12th. So just that's a nice way to think of it is to actually try to visualize it. Or at least when you apply the rule, make sure you justify it with a simple example. Like, oh, here, it doesn't work, but that's what it means. Okay. So this would give us now plus 8 times x to the 35th over 1 times 2 over x to the 15th. Da, da, da. And then this is 256. And in the denominator, we have x to the 15th raised to the 8th, so the x to the 120. And then this is equal to x to the 40th plus 16 x to the 20th. There's a 15 x's that cancel out with those. And it keeps going all the way until you get to 256 for the x to the 20, 120. Any questions on, nice, Andrew, very good. Any questions on how this pattern works out? And the key is, the key idea is that like, usually when we do this type of expansion, this number is pretty simple. So it just ends up being a simple constant. However, in this case, it's got an x in the denominator. So it's going to have a really huge power of x in the denominator. What that suggests is that somewhere in the middle here, we're just going to end up with an expression where all the x's cancel out, and that would be our constant. So that's what I'm thinking. When I see this type of problem, and I see an x in the denominator, x in the numerator, and it's all being flowed out, I got to look for some middle term where they all cancel. And I'm going to give you a really simple approach that doesn't, may not work for harder ratios, but in this case, you can kind of basically do it by inspection. So the first thing is, I think of this as quantity A and quantity B. And what I'm thinking is I want to get just the right amount of each one of A and B, like the right exponent of them, so that the x's will cancel. And then when I'm thinking about that, I got to say, well, that means that I got to have, there's different choices of A and B to make the x's cancel, but I got to just pick one that's in the right proportion. So what proportion do A and B have to be in? The number of A's and the number of B's have to be in order for them to cancel. So what is the proportion of A's, the number of A's, A terms, to the number of B terms? How many things that look like A do I need to cancel out things that look like B? For the x's to cancel. What ratio do they need to be? Does everyone see? That's a really simple ratio. How can I use things that look like A to cancel out things that look like B? The ratio, perfect. But they got to be in a ratio 3 to 1. So the exponent of A has to be 3 times bigger than the exponent of B. Right? Because x to the 5th has to be raised to the 3rd power in order to make it cancel out with a single x to the 5th. Okay, so here's the game. Can you think of two numbers, m and n, that add up to 8? Because I want to overall think of two numbers that add up to 8, because that's anytime I do it, something in the expansion, I'm always doing exponents that add up to 8, and are in a 3-to-1 ratio. And you just kind of take a moment to think about that and think of two numbers. You think of two numbers that add up to 8, but one of them is 3 times the size of the other. And I'll show you, you can also set this up with a system, but I find that just kind of, if you can think of this, the two numbers that you have to do it, then you can do it pretty quick. What two numbers add up to 8, because we've got to think of two numbers that add up to 8, but they're in a 3-to-1 ratio. Nice. Dana, what did you suggest?
6 and 2.
Yeah, and how did you do it?
Just because 6 plus 2 equals 8, and then 6 choose 2 kind of like simplifies to 3 choose 1.
Well, yeah, we're not even doing anything with choose. We're just saying like ratio, like 3-to-1.
Sorry. Yeah, I meant ratio.
Yeah, exactly. That's right. And you could do this with a system if you needed to. The system, when things are in ratio of 3-to-1, that tells you that m is equal to 3n. That's all. Like there's a simple relation, and then you can solve it with a system. But I think that's overkill. Just think of two numbers. Like it should just come to you. You can do a guess and check, like what two numbers would fall in that ratio. So the answer is m equals 6 and n equals 2. So let's just plug it in and double check that we can make that work. So what we do here is we write x to the 5th raised to the 6th all over 2x to the 15th squared. And then what are we missing in the front here? What do we need to write down in order for this to be a part of the expansion? So I got 6 a terms and 2 b terms. But what am I missing overall? What do I need to definitely have in order for this to be equal to the expansion? Oh, you know what? Yeah, good point. I actually dropped this. I'm sorry, I dropped this subtraction sign because I didn't want to make it more complicated than it already was. But if there was a subtraction sign in here, let's say, I would put it in here for sure. It wouldn't make a difference, but it would be the proper thing to do. But I change it to a plus. What else do I need to include if I'm doing some expansion and I'm looking at the term that has 6 a's? That's why I have 6 here, and 2 of these guys. That's what I do here. What else do I want to include in that overall expression? Nice. Yes. Colette, what do you suggest?
I said 8 choose 2.
Perfect. Yeah, because anytime you have something in the expansion, right, you always have to consider all the ways that you can make words with 6 of terms that look like the A term and 2 terms that look like the B term. So it's basically like saying have 8 choose 2 ways to invite 2 friends to go to the movie with you out of 8, or two places to put the B term and put the rest 6 would be the A term. That's it. So just look at what happens here. 8 choose 2 is 8 times 7 over 2 times 1 times x to the 30th times 4 over x to the 30th. So these cancel. And then you're just left with these cancel as well, leaving it to 4. So we just left with the number 60. So somewhere in this expansion, I believe it will even be the next one. It'll just be the number 60. How do you guys feel about this approach? Any questions about it? Oh, wait, I forgot to set it. No, I'm sorry, guys. Okay, 8 choose 2 is 28 times 4. 28 times 4. 28 times 4 is how does that sound? Does that help with kind of the idea what we're doing there and how it works out? And this, okay, nice. It looks harder than it is. I think that's the issue with these exponents. But if you just remember how the exponents work and what you're targeting, it's actually turns out to be pretty nice. All right, last few minutes here. I want to show you some patterns that are in Pascal's triangle. So just to remind you, Pascal's triangle comes from rows of all the combinations. So we start with 0 choose 0, and do 1 choose 0, 1 choose 1. Then you can do 1 choose 1. Oh, sorry, 2 choose 1. 2 choose 0, 2 choose 1, then 2 choose 2. Then 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3. So you get it from all the binomial coefficients. And the triangle, when you actually draw it out, you can different. So when you draw out the triangle, you put the numbers in, you get 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 6, 4, and 1, 5, 10, 10, 5. And the thing is, you can calculate each row just by knowing the combinations in that row. But there's also another way involving the two numbers in the triangle that are just above it, combining them to get you the new number. That's a way you can do it if you know the previous rows. You can kind of add the two numbers that are next to each other and get them to the next one. And then the 1 just adds up with 0 because there's 0 outside, maybe. You can think of it like that. Okay, so here's some neat patterns. There's lots of fascinating patterns. But here's something related to the numbers. What do you guys notice about these numbers here? These diagonals. You guys notice anything interesting? Yeah, how would you describe these diagonals? What's happening? What's the pattern that's happening? In particular, does anyone see an interesting pattern for this diagonal? 1, 3, 6, 10.
I think the first one obviously is all ones, and then the second one goes up 1, 2, 3, 4, 5. And then the third one, I think those are triangular numbers.
Exactly, nice. That's right. So what's cool is that these are related to numbers that come from drawing shapes in different dimensions. So, you know, in 0 dimensions, the only shape you can draw is a single dot. In one-dimensional kind of shapes are line segments. So if you can draw 1 dot, you can draw a line segment with 2 dots, and you can also draw a line segment with 3 dots, and so forth. And this will just be a regular sequence drawing one by one. But if you want to draw a 2-dimensional shapes using dots, and sort of the simplest two-dimensional shape that you can make that actually has an area is a triangle. And it's exactly like Colette said, you can draw these things that are called triangular numbers. So if you notice, the interesting thing about triangular numbers is that the thing that you're adding is always increasing by 1. So previously, above, we're just increasing by the same amount, but here, we're gradually increasing our stepping by 1 step itself. This is 3, then this is 4, and then the last term would be +5. So 2-dimensional way of interpreting those numbers is as a dot, as parts of a triangle. So 1, 3. And if you make it a little bigger, you gotta add a new base. So we get 1, 3, 6, and then we do it one more time. 1, 2, 2, 3, 4. This would be a little 2 minutes. So these are called, like Colette said, these are called the triangular numbers. Okay, does anyone want to take a guess about this pattern, 1, 4, 10? And this will be the last thing. What do you guys think? Any thoughts on 1, 4, 10? How it would continue, and what picture we could draw that would represent 1, 4, 10? Nice, Dimitri. Yeah. What'd you come up with?
So if you just extend that into the 3rd dimension, you have the very tip, which is just like a pyramid. You have the very tip, which is 1, and then you have 4 underneath that to support that, and you have 10 to support those.
Yeah, so this is a special pyramid called the tetrahedron. And it's just like a triangle is the simplest thing you can make that's 2-dimensional. A tetrahedron is the simplest type of shape that requires the fewest vertices, like on the corners, to actually make a 3D polyhedron, a 3D shape. And if you extend it a little bit to make one a little bit bigger, you'd have your 3 dots here, but then they would each extend a little bit more. If there would be something else on the boundary here, there would be another point on the boundary here, and another point on the boundary here. So we get these guys connect like that. And this goes like this. And the bottom there. And let's see. I'm not super happy with that drawing, but yeah. Background, and then there's this is also the background, and then there's this. This is the main. And if you look at that, that's the triangle. That's like adding the next triangle here, the number 6 to the previous 4. So you get 1, 4. And all right, guys, and these are called tetrahedral numbers. And what's really crazy is you can think about the next diagonal as numbers that represent probably like shapes in the fourth dimension, which is hard to visualize, but those would be the number of dots if you try to keep making that shape bigger and bigger. So yeah, this is one neat thing that is in Pascal's drawing, and there's a lot more. And then I think maybe on Tuesday I'll continue talking about a few of them. All right. So yeah, do you guys have any questions about these patterns or about the test or anything like that?
I have a question.
Yeah.
I don't really see how you get 10 for that like last one, the 3-dimensional one.
Yeah. Okay, so yeah, so my picture wasn't the best. So are you okay with the 4, right?
Yeah.
So the 4 is still here. That's right there. Underneath it, I drew another bigger triangle. So I extended this to a corner, I extended that for a corner, and I extended that one for a corner. There's a bigger triangle underneath this main triangle. Maybe I can draw it. Maybe there's a triangle right here. Then there's another triangle right here. And that triangle has is the same as this triangle. It's just laying down.
Are we counting? So we're counting like the dots?
Yeah, you're counting all the dots, exactly.
Got it. So you would be counting 6 plus 4.
Exactly, that's right.
Okay, got it. I thought we were counting the vertices. Okay.
No, not the vertices, just the dots. It's just like the kind of triangular numbers. When you build them up like this, they're always going to be a triangular shape, but you're always interested in counting, like, you just add the next level to get the count the total number. Yeah, so it's a really amazing pattern that these combinations are related to kind of these pictures in geometry. And there's a lot of things, a lot of fascinating things with triangular numbers and all these sort of geometric numbers. And if anyone thinks of a nice way to think about the next dimension, I would be curious to hear your thoughts. So, I think that's harder to visualize. All right, guys. I hope you have a great weekend. If we already talked and I gave you a grade, I'm going to return some exams. If you get your exam back, you don't have to do the retake. And if you felt like you did well, but we didn't get a chance to talk, message me so maybe we can meet tomorrow or something like that. And otherwise, I will see you guys on Tuesday. And I'm here if you have any questions. I'm happy to hang out for a little bit more.
Thank you. Have a good weekend.
You too. Bye, Clyde.
I have a quick question.
Yeah, definitely.
In our one-on-one, I in the last constant term problem, I had a little trouble with the fractions and variables, and you told me you'd give me some Khan Academy assignments to do just to practice.
Oh yeah. Oh, okay. Okay. Let me take a look. One second. But Dan, do you feel after kind of last 2 classes, you feel a little bit more comfortable with the expansion stuff?
Yeah, I feel a little more comfortable, but it's still like, it's still like a little bit of practice just to kind of make sure I understand it completely.
Definitely. Okay.
The fractions and the exponents with like variables and the fractions. That makes sense. It was like one of the last steps in the constant term problem.
Let me take a look here. Ben, is your last name Utopia?
Yeah.
Okay, good. Just make sure I was right. Yeah, so let me just see kind of where you were with the. Wait, only one comment I would make. I think you did a really great job. I see only one comment to make on your steps. So it's just when you when you plug in, especially when you plug in stuff that have a minus sign, use parentheses.
Okay.
Because otherwise, I saw you write something like this, like you wanted to plug in, you wanted to do for number, was it number 10 or something? You needed to expand the whole thing, and you had, so it looks like you're really good on the concept, but I'm not concerned about your understanding of the concept. It looks like you wanted to do this, minus 2 to the third, or something like this. There was a term I saw like this. Let me just see.